Welcome back. Today, the problem we'll be looking at is search in rotated sorted array. The problem states that there is an integer array nums sorted in ascending order with distinct values. Prior to being passed to a function, nums is possibly rotated at an unknown pivot index k, where k is a number between 1 and the length of the array, such that the resulting array is this 0 indexed. For example, 0, 1, 2, 4, 5, 6, 7 might become 4, 5, 6, 7, 0, 1, 2. Essentially what this means is the array might be shifted to the right. It might be shifted a number of times. Given an array nums after the possible rotation and an integer target, return the index of target if it is in nums, or -1 if it is not in nums. And you must write an algorithm with O of log n runtime complexity. Example 1 here, we have nums equal to this array, target equals to 0, and so we return 4 as 4 is the index of 0. Example 2, target is 3. We don't have number 3 in this array, therefore we return -1. Similarly in example 3. This problem is trivial if we want to solve it in O of n runtime complexity. All we have to do in that case is simply loop through the array and at each iteration check if the current element equals to target. If it is, we return the index that iteration. However, this problem states that we must solve this problem in O of log n time complexity. And this is a huge hint for us, again, because every time we see O of log n and a sorted array, that is a huge hint to us as to saying that we should use binary search. So let's go to the whiteboard and see how we can solve this problem in binary search. Given the input array 4, 5, 6, 7, 0, 1, 2. Notice that this is sorted, so this is sorted and shifted. We start from 0, we go to 1, 2, and then we come back from the beginning, 4, 5, 6, and 7. And let's say the target equals to 0. We want the answer 4 because that's the index of 0. So how can we do this? We know that we need to use binary search for this problem, but a normal binary search wouldn't solve this problem because the array is shifted. So what we need to do here is, at each iteration, before we perform binary search, we need to find out whether the left or the right part is ascending. For instance, let's look at this concretely. For binary search, we have our left and right pointers. At each iteration, we calculate the mid pointer, in which case it would be 0 plus 6. 0 plus 6 divided by 2, 0 plus 6. Integer division, so that will be 3, and its midpointer would be 7. This would be our midpointer for the first iteration. Now, we want to perform binary search on this array, but if we use the right part of it, we cannot perform an accurate binary search because the array is not sorted anymore. If we use 7, 0, 1, 2, that is not a sorted array. Hence, what we do is we use the left part of this array, which is sorted. That would be 4, 5, 6, and 7. Okay, to reiterate, now we have mid pointer pointing at 7, and we want to use the ascending part of the array, which is 4, 5, 6, 7. How do we do this? We check. How do we find the ascending part of the array? We check if nums left. So if nums MP is greater than or equal to nums left, that means it's left ascending, right? Because the entire array itself is sorted and shifted. However, if we know that nums MP is greater than or equal to nums left, as in this case, we know that this will be left ascending. If it is left ascending, what do we do? We use this and we check if the target is in this range. Concretely, this is what it looks like. If nums left is less than or equal to target, and target is less than or equal to nums mid pointer, then we know we have to shift the right pointer to MP minus 1. Okay, why is this the case? Okay, let's say instead of 0 and 4 we have 5 and the output would be 1. We know that 5 is in between 4 and 7. So this statement here returns true. If it returns true, we simply need to shift the right pointer to 6, and we don't shift it to 7, we don't shift it to MP because of this inequality here. This is strictly less than and not strictly less than or equal to. Because it's strictly less than, we know that target cannot be equal to MP. Therefore, we shift right equals MP minus 1. Else, let's say we have 1. And the output should be 0, 1, 2, 3, 4, 5. Be 5. Okay, here we know that the target is 1, and 1 is not in between 4 and 7. So what do? We shift the left pointer instead. So this is how we can take advantage of the left ascending pointer, left ascending part of the array, and use that to perform binary search, which will give us a log n time complexity. Notice how this is only left ascending. We also have to do a part where it is right ascending, but it's essentially the same thing, except this time you're using the right part of the array instead of the left part. Also, before any of this, you need to check if mid pointer, so if nums mid pointer is equal to target or not. If it is, we simply return it, and we don't have to do any of this, right? So let's go to the code walkthrough and see a concrete implementation. All right, So first of all, we need to define 2 pointers, be left and right. And then to perform binary search, we do while left less than or equal to right. Notice how it's less than or equal to and not simply less than. The reason is because when left and right are equal to each other, there's a possibility that that is the number that is equal to target. That's why we want to check for when left is equal to right. And then we have our mid pointer. This would be left plus right, integer divided by 2. Next we have if nums mid equal target. So here is when we check. Here's when we check if the mid pointer is equal to target. If it is, then we're done. We simply return the index of the current element, which is mid. If nums mid is greater than or equal to nums left, so this would be left ascending, right? Remember how we said the array is sorted, and if nums mid, in our example on the whiteboard, this would be 7, is greater than or equal to nums left, which is 4. If that's the case, what do? We want to use the left part to perform binary search. And that would be if nums left also notice how we don't have an equal sign here. That's because if it were equal to nums mid, we would have returned mid out here. Therefore, we don't need to put an equal sign there. So this would be left ascending, and we check if target is in between nums left and nums mid. If it is, we update our right pointer. Else, we do left equals to mid plus 1. And again, do the same thing, but this time, this else block here would be right ascending. So if nums mid is less than target, and this is less than or equal to nums right, left or equal to mid plus 1. Else right equals to mid minus 1. Again, in this else block, we have a right ascending part. Since we know it's right ascending, we use nums mid and nums right to capture the boundaries of the right ascending part, and we check if target is in between those two. If it is, then we update the left pointer to equal mid plus 1, else we update the right pointer to equal to mid minus 1. And then we repeat this process until left is greater than right. After that, if we don't have an answer, we simply return -1. That means the number target is not in the nums array. Let's see if this works. Okay, that got accepted. Let's see. Okay, that's a success too. Well, that's it for this video, and if you liked the video, make sure to like, comment, and subscribe. Thank you for listening. I'll see you next time.